I do have CDs. Sort of like the presentation, first part of the presentation was from this CD. They're available for you, so maybe if you're interested, they're just here. Just write one or more than one. There's more than what I presented. It's of course not necessarily just for physicists, but it's relatively complete. So feel free to come down and get one. Yes. How much?
Good idea.
In terms of weight? It was several tenths of grams, not much. Yes.
That's hundreds of kilograms, right?
Roughly, yeah.
And how much does this thing going to have in the reactor and which could be used?
In ITER, I comment on that because it's one of the problems that tritium is sort of pumped by the walls and kept there. I think in ITER the limit, which is the experimental reactor limit, is 500 grams or something like that, inventory limit. So it cannot be more than that at a given time in a machine.
But that's really a very large amount. Isn't this when you talk about the safety? Saying that fusion energy would be so safe, isn't this a very major concern because if that escaped,
well, I mean accumulated over all the months of exploitation at JET. I don't mean at any given time. So I think JET is reprocessed of the order of 100 grams. I should check on that figure, but I think that's more or less
Yeah, but even ITER, for instance, you're going to have half a kilogram of tritium at one given moment, and something happened with that escape. That would be a very, very dangerous thing, wouldn't it?
I don't know exactly the implication, but I don't think that's a major concern really. The tritium will be reprocessed by lithium, so in fact.
Yeah, I understand. Of course, you don't have tons of it, but still half a kilogram is a very large amount.
But that's because we don't breed tritium from lithium at present. So in a reactor, you don't have that. But I'll check on those figures and come back to you. Okay, so in this third lecture, I will continue discussing the challenges in magnetic fusion let's say for a physicist, because there are obviously technological challenges and challenges related to handling tritium. Macroscopic equilibrium instability, we have seen the ideal MHD situation. Now we look at what happens in the case of resistive instabilities. And then, if you agree, I will expand on the basic physics problem that's related to MHD in tokamaks and also in space, which is the so-called magnetic reconnection problem. It's sort of a little diversion, but I hope it'll be interesting to see what basic problems we are attacking and what they are, what do they have in common with space problems. So I should put this on. So first of all, an example of how we control a resistive MHD instability. I say this is acting on a relatively long time scale, so we have the hope to feedback control it. And this is an experiment in US, which has loops that detect the instability by induced current, the radial field related to the instability. And then there's an active coil or an active system of coils that feeds back a field correction to actually eliminate that instability. In this case is called a resistive wall mode, but there are so many instabilities, there's a large number of names I will not ask you to remember. This is just to show that this technique does work and the sort of time scale over which it works. This is the beta of the plasma. It's sort of normalized, but anyway, it's the value of beta of the plasma. And the black line is in the absence of this feedback. As the instability comes in, this is the plasma rotation. It sort of breaks the plasma rotation and kills the plasma beta. If it was an energy producing plasma, it would be a disaster. Now we turn this coil on, and it's automatically connected to this loop sensor, and it will drive a current. There's some phase here because the instability is not always the same place and it's moving, so we need to be able also to change the phase. And that comes on and puts back the beta on the right spot. So it really takes you to a good, keeps you in a good regime for beta. So we do know what to do about some resistive instabilities. And this is my digression a little bit. It's very important in tokamaks, but we'll see it has implications on other situations. It's sort of something in between ideal and resistive. It's the so-called sawtooth instability. Now we observe here the temperature measured in the tokamak, generally tokamak. All tokamaks actually do this. The temperature looks like sawtoothing, we call it. So there are sudden collapses in it. This is a reconstruction from an X-ray emission. It's tomographic reconstruction of X-ray emission on a TCV tokamak over one cycle of this instability. And you see at the top here, before it happens, the plasma is nice and hot. Red means hot. And suddenly, puff, the plasma collapses over a very short time scale, and the heat is lost. So it's not that good for the fusion reactivity. And that happens in a plasma core. So what happens after a long research, we sort of understand roughly what happens. There is a breaking. This is not a great picture, but there is a breaking in the field structure. So we have built a cage over which confines the plasma well, but then the plasma finds a way through this instability to make a hole in that cage, if you like, because the field structure is sort of at one given point broken. The field lines are so cut as if you were cutting them with scissors and reconnected on the other side. This is what this is called a magnetic reconnection. There's a change in the topology, in the structure of the field line, very locally. So you immediately say, okay, but you just told us that it takes a long time to separate the plasma from the field. So how can that happen over such a short time scale? Well, that's indeed one of the mysteries of this problem. That's why we do research on this subject. To expand a little bit on that, as I say, this is called magnetic reconnection. It's a change in the field topology in the presence of plasma. And in fact, it's all over the place in the plasmas in the universe. The sun, as you know, has these instabilities. It's a solar flare that comes out. This is embedded in the magnetic field. There's current circulating here. But in order for it to be ejected, it's what's called the coronal mass ejection. You need to cut the field lines and lines and reconnect them. So there's a reconnection event there. Then the solar wind is generated and it's emitted towards the rest of the solar system. It comes towards the Earth. What does it do? Depending on magnetic field that he has, because he has carried it with it from the surface of the sun, it interacts with the dipole field of the Earth. This is the dipole field of the Earth. Is just a pictorial view. It modifies it, and then on the geomagnetic tail, which is sort of here on the night side of the Earth, it does the same thing that it does in tokamaks. It locally breaks the field lines. It locally breaks the field lines, and by doing that, it manages to then find a way inside the dipole field, inside our own sort of protective field. And then once the plasma comes in, this is a result of a solar flare initially, then becomes a coronal mass ejection, and then solar wind comes down, and then when it breaks, this is called a magnetic substorm. It comes back into the ionosphere of the Earth, is guided by the dipole field down, and it impinges on the two poles. It produces radiation there, and that's what the aurora is. This is the aurora picture of its borealis from a space shuttle. This physics of that is in fact very similar to what we have just seen in a tokamak. These reconnection events are also called internal relaxation. So why is it a mystery? This is a little bit of repetition here. Resistivity is very small. Plasma and field are frozen together. You should not have any reconnection. Now you put resistivity in, and you have a resistive time, which is basically the time that it takes for the field to diffuse away from the plasma, and it's related to a characteristic length, and you can calculate that. So why is that an open question? Is classical physics? Well, it's an open question because if you look at the value of the resistive time, in Tokamak it's over 10 seconds. Tokamak is very hot, so it's not collisional. Reconnection time occurs over 10 or 50 microseconds, orders of magnitude shorter. Solar flares should occur over 10,000 years, and in fact the time scales once they are ejected, it's over the 10 to 20 minutes. And substorms is even actually pointless to calculate the resistive time. There's too little plasma there, and the typical time scale for that is half an hour. So really there's something wrong in our understanding here. So there are two ideas. One says, okay, I convert all the energy in the field into plasma flow. And plasma flows at the fundamental speed in the plasma is called Alfvén speed. It doesn't really matter, but that fundamental speed will also give you a time that doesn't work at all with what you observe. In this case, it will be far too short. So this idea is not working. And now a better idea is to take a model that says, okay, watch out for what characteristic length you take, because this may happen very locally, and so all the plasma is decoupled very locally for the magnetic field, and so it has to go through a small amount of distance, and hence the time may be short. But in fact, if you really do the physics calculation here, you come out with a characteristic time that's orders of magnitude still far too long. So we need to investigate what causes reconnection, what we call fast reconnection, not related to collisions. And we could look at that in a laboratory. So I'll show you an example of a laboratory experiment that observes phenomena that are of interest of fusion in space, but it doesn't produce fusion parameters. Can the fast collisionless be observed, or is really our interpretation is totally wrong? Can it be steady state? Is it intermittent? Why does it happen suddenly and not all the time? And most importantly, what's the origin of this fast time scale? In other words, what breaks this frozen in law? What, other than collision, breaks this coupling between the plasma and the flux? So this is an experiment we developed in MIT in US to study the plasma response to reconnection. So this is a relatively small experiment for plasma physics standards, and of course for particle physics standards too. It's investigating one specific phenomenon that occurs in fusion devices and in space. But it does that in a much cheaper way than than fusion devices and space. You have sort of little magnetic probes that pick up the local currents. You don't need to reconstruct the equilibrium. You go and measure directly, and then electrostatic probes, and you can put as many as you like, depending on how many sort of graduate students you have. But each one of them is equivalent to having a satellite at the right spot at the right time to measure the reconnection. Having a satellite and a geomagnetic tail and knowing where reconnection occurs is very difficult. So nowadays there are missions that have 2 or 3 satellites more or less in the right spot, but that means you have 2 or 3 points. And they fly by, because it's a dynamical problem, it's very difficult to understand the physics. So this is an example of what we do in a laboratory. This is just to show a structure of the machine. Reconnection is driven by external fields in the center of the device. This is the plasma that you form in the center of the device. Don't look at the other details, they're not important. So you form the plasma, you hold it in place, and then you drive reconnection and see what the plasma response to it can be. Let's see how reconnection is driven in the plasma. You create an electric field perpendicular to the plane here. If you have an electric field perpendicular to the plane, remember you have an E cross B. The B field is in this shape, so it's we call a cusp field. And therefore, you sort of squeeze the plasma here and pull it on the other two sides. In other words, you sort of create an artificial geomagnetic tail. The technical details here are not important. You do that over a relatively fast time scale, and you smash the plasma from the two sides together. So the question is, what happens when you do that? Here is what you may expect that happens. You have the colloidal flux, which sort of represents the plasma as we've seen. Everywhere is a good representation except where the field lines are broken, so except in the middle. You can either have an ideal MHD case in which you see absolutely no reconnection at all, so it doesn't allow for reconnection because you cannot decouple field lines from the plasma. So the flux from the different sides remains on the different sides. So this would prevent, for example, a solar wind from coming inside the dipole field of the Earth. So this is one possibility that we expect. This is a theoretical calculation. It's not reality. Oops. The other possibility is if the plasma is allowing very, very fast reconnection. So all the flux from one side can go. So no resistance to this breaking of the field line structures, as if, in fact, if there was no plasma at all. So obviously reality is sort of in between. We need to understand exactly how, and this is an example. I don't ask you to go into the details, but this is an example of what one can actually measure in a device like that, reconstruct exactly the current density that's locally, and reconstruct from local field probes the exact structure of the field lines at any given time. So one can see whether reconnection can occur, at what speed it occurs, is that speed compatible with collisional theory or not? And so one can extrapolate the physics that can then be used for understanding the reconnection events in space and in the tokamaks. So the current channel is produced. In this case, we see that, for example, the current channel, which is this red spot, although the drive is constant, actually is produced at the beginning and then disappears. So this is already a very interesting finding. It's not expected. It wasn't expected. Although you provide the same drive, it can only last, the resistance of the plasma to the reconnection can only last for some time. So there is no steady state possible. Then one can look at the details. What is the cause of fast reconnection? What breaks the frozen-in law? And one can look at the region where E dot B is not zero, which is the region in which the two things, the plasma and the field, can be decoupled. So that's what we call the diffusion region. One can measure it directly experimentally and scale that and understand what the quantitative response of the plasma is in this region. And finally, one can look at the different terms, think that one can obviously not do either in space or in fusion devices, and understand what the mechanism is that breaks the frozen-in law. When we write the Ohm's law, we have seen that before in the MHD model, we have taken only the first part. In fact, there are other terms we have neglected, and these other terms are related to the whole term, to the inertia of the electrons, and to the pressure gradients in the electrons. So we can measure each term and identify which one may be responsible for this effect, and possibly suggest ways to control that effect. We now understand that's related to this term, pressure in the plasma, pressure gradient in the plasma. And in fact, it's a tensor, so it's not simply a scalar here. So it is the terms that are related to particle orbit effect come in, play a role in the reconnection. So in other words, we cannot hope to describe reconnection with a macroscopic model, which is what people have done so far, have tried to do so far. So just to conclude this part, yes, we have observed and we can observe reconnection not due to collisions in the lab. We have a current that's much anomalous, in other words, not explained by collisions. And in fact, it's not even a constant ratio between field and current, so you can't even define a resistivity, which has been sort of the mistake done in the past, or mistake in the sense that people couldn't do much else. Reconnection is intermittent even with a steady drive, And from the dynamical evolution of the current and its profile, one can understand what the mechanism is behind it. And again, by exploring the different terms on the law that relates field and current, the Ohm's law, one can identify the mechanism, or at least the area where to look for mechanisms that break this Rosenine law. In other words, decouple the plasma from the field and allow sudden breaking in the magnetic cage. Again, in Tokamak is for plasma to escape. In the geomagnetic tail is for plasma from the outside universe to come in. Back to Tokamak problems, a little bit more back to practical. This was a diversion in what we call basic plasma physics. It's part of the activities in our program is to attack these problems and a relatively fundamental level and try to give the answers back to fusion. Now we're still dealing with these instabilities. The plasma is very complicated. It has so many relaxation processes that can go on that we really have to be careful about counting all of them. This is a problem that we have recently identified. There are sawtooth oscillations in the plasma we have just seen. They eject a little bit of plasma from the core, but in many cases they are actually benign. In other words, they reduce the fusion reactivity, but not so much. It's not that dramatic an effect because the redistribution is only local. Now there is one other problem. Here are the sawtooth instabilities. There are fast particles in the plasma. Plasma contains particles that are not thermalized. For example, alpha particles. We must contain those because they sustain reactivity. What do they do to these sawtooth? Well, again, you have to do the calculation in MHD. It's complicated, but they make the period much longer. The period much longer corresponding to what we call a stabilization. It's not a very good choice of word, by the way. You see in a moment why. Because if the period is much longer, then the collapse is also much longer. You sort of build up to a bigger energy content, and then the collapse will be much bigger. If the collapse is much bigger, then it's not ignored by the plasma. The collapse is much bigger. It provides a seed to another instability. So you see the kind of challenges we face. This instability now collapses, it perturbs the plasma at a given point, and then there's another instability or classes of instability that takes place. It's called an NTM. Again, we are champions in acronyms. I wish it wasn't the case. It's a neoclassical tearing mode if people are interested. But anyway, it's another instability that's resistive, so relatively slow and might have a hope to control it. We'll see in a moment. What does that do? But that's much more damaging than the first one because it tears the B field structure in the same way, but it does that over a much larger region. So it makes a big hole for plasma to escape and degrades, therefore, the confinement. And you see that is the energy content. This is a jet pulse again. This is the energy content. No problem with the sawtooth, okay? The sawtooth keep the energy a bit less than what it could be without them, but it's not too big a problem. But once you have this collapse, then leads to this instability, energy content goes down. Then again, you stabilize here, and then energy content tends to go up, and then collapse, and another instability here, and again, you lose energy from the plasma. So this is a problem that needs to be attacked. What to do about these instabilities? First of all, a little word on what they are. They're called neoclassical tearing modes. We don't need to go into the theory, which is relatively complicated, but they are islands, so the structure is not nice and smooth around, but there is what we call an island, a different structure of magnetic field locally. The instability is sustained once it's driven by a lack of current in a region of the island. So in other words, the current should be nicely and smooth from the edge to the core, increasing. But instead of doing that, or the pressure, but instead of doing that, let's say this is the current, in the island there's suddenly no current because the particles will circulate around and therefore they will not be able to carry the current. So that lack of current is the mechanism for the instability to be sustained. So again, this is an example of the stability taking place. This is the amplitude of it measured from an external magnetic perturbation. It grows. The beta, another measurement of the plasma performance, goes down. It was going up and then reaching the limit of instability, and then it's sort of killed by the instability. So it's really not good for a reactor. This is a macroscopic measurement. It's not a local measurement of performance. It's a macroscopic reactor performance measurement. So we need to try and avoid them, or at least reduce their effect. There are two ways to do that. This is an example. It's not the only instability we're facing, but it's one of the most important ones for future reactors. Okay, first of all, we can avoid them by controlling the saw teeth. In other words, trying to keep their period short. And we can do that with radio frequency waves. I'll spare you the details, but I showed the example of that. That it may work. So I say these are relatively benign. We want to avoid the big guys that are so-called monster, and then they have a big collapse. So what do we do? Well, we have some sort of coupling of ion cyclotron waves that resonate with the ions. That locally drives a current that removes the stabilization effect from the particles, and sort of leads to even smaller oscillations here. So no monsters anymore. So this is a good method, although it's not so easy to apply in a real reactor, because you need a lot of power to do that, and you really don't want to waste power to do this kind of exercise. So it's a demonstration that we understand what goes on, but it's not necessarily the good solution. Another way to do it is to act locally. I say, okay, I have a problem with this island, this little perturbation in the plasma. It's not so little actually, but it's a perturbation in the plasma in which some current is missing. So what can I do to avoid that grows? Well, I put myself from outside, some current just there. Replace the missing current. If I do that, I can stabilize the mode. Well, it's not a trivial thing to do. This is in general here there are megaamperes, several megaamperes circulating, so the missing current is not a order of amperes, it's a lot of current. And it's relatively localized, so I need something that drives reasonable amount of current and relatively localized. And I can actually follow, maybe even in real time, the instability and inject where I need that. It sounds like science fiction, but in fact it's done. I wouldn't say routinely, but it's done and it works. And it's done by the electron cyclotron heating method, which I have shown an example of from Lausanne. This is in another example. This is from San Diego in California. And in this case, a mode is detected, an NTM is detected, and then you shoot a beam. The higher the frequency, the smaller the wavelength, obviously, the more local you can be. So going with ion cyclotron waves wouldn't work, but going with electron cyclotron waves would work, because they can be focused down locally and replace, by giving enough angle of injection, the missing current very locally in the island. The island is detected by magnetic probes outside, and once you do that, you in fact get rid of the instability. If you don't believe me, this is the result. Here again we have a plasma that's heated, it's several megawatts of neutron beams just to keep the plasma hot. This is the beta that comes up, so we sort of nicely cruising towards very good performance, but instability comes in. And this is a measurement of the instability amplitude. Comes in, then varies a little bit. Then we need a little bit of time to understand where it is and fire our beams. These are, again, beams in I think it's 80 gigahertz frequency range. So we put the power on. We're not perfectly on the right spot at the beginning, but we're tracking now. And then after a little while, we are on the right spot. And look at the instability, and it goes away. We are driving the current in that little island where it should be. Instability goes away. What happens to beta? Our performance measurement, well, it goes up. So then at the end, this is to show that it's not 100% of it is in the pocket, but at the end, the plasma moves a little bit and we are losing the positioning here. So we're shooting slightly off the target, and so the mode comes back again, and the beta also starts going down again. So this is a technique that's indeed foreseen, maybe not for a real reactor, maybe it would be smarter than that, but at least for the proof of principle reactor, which is ITER. And you need several megawatts, so I think it's the order of 10 to 20 megawatts of power to do that. It's a lot of power that's deposited locally because you need to drive, even though it's local, a lot of current. But that's done. It's also a pulse, so it's not a lot of energy. It's a lot of power, but it's not a lot of energy. So in the overall balance, it's not a big problem. The only problem is really to keep it stable. So the other topic I wanted to address today, I'll address part of it and then continue on it tomorrow, is a problem which I believe it might not be the sexiest one for a physicist necessarily, but I believe is one of the most important ones, and that is the interaction of the plasma with the surrounding wall. You need to have an enormous amount of conditions satisfied at the same time for the machine to work related to the interaction with the wall. What are the issues? You need to withstand power fluxes. You need to have the wall that doesn't melt, is not too eroded by the plasma. Remember that, let's say a reactor of the size of what we anticipate for the next step is of order of 1,000 cubic meters. So it's like the plasma volumes is like a medium-sized villa. And in that you have half a gigawatt of power. So you need to have something that withstands that power. That needs to be, of course, guaranteed in steady state, but this is not a worry, not so much a worry, I should say, at least not for my understanding. The problem is when you have instabilities that happen at the edge, and I'll discuss that probably not today but tomorrow, and what to do about them. You need to keep the plasma pure. You need to keep the plasma pure because ignition will depend and fusion gain will depend on that. Why? Well, remember, brainstorming radiation is one of the loss channels we are fighting against. That depends on z squared. The power emitted depends on z squared. And here is the cross section. So it's the power density here as a function of the temperature. And you see that the bremsstrahlung will be killing you if you are either too low temperature, which we know we cannot be, or if you move out this line, up this line by having larger and larger z. So if you have larger and larger z, this line goes up with z squared, and so the region of temperature in which you can work becomes more and more difficult. You have to go to higher and higher temperature in order for the DT fusion power to be larger than the loss power. Another way of looking at that is here the minimum ignition temperature is sort of a summary of this plot, if you like. In this case, as a function of the impurity concentration in the plasma, and this is for different Z, so for different possible impurities you have oxygen, silicon, iron, molybdenum, and so on. So obviously, if you have a high Z material, only very small impurity concentration will make the ignition temperature that you need very, very large. So this is the challenge, is to have low impurity concentration in the plasma core and low Z materials that may be spattered from the walls into the core in order to make our life a little bit easier to reach ignition or to reach high fusion gain. Sort of the same problem. We want to minimize the retention of tritium. We don't want the tritium to be absorbed by the walls, because then we'll reach the inventory limit without that amount being useful at all. It's just sitting there in the wall. We need to exhaust, and again, this is a major problem. We need to exhaust power and particles. We need to, of course, get the power out. First surface will be probably solid. It is solid in the present day concept. And then is in contact with the fluid transfer medium, which will then take the heat outside and, of course, generate electricity. We need to exhaust particles. Once the particles have burnt, in a sense, we call the ashes, for example, the alphas, have given all the energy to the fuel ions, where we don't want them anymore. They're not useful. They dilute the fuel ions themselves and they reduce the fusion power. So they have to be removed. So that leads me to a concept of, if you want, design in the external region of the plasma, which is called the divertor. The idea of it being relatively simple, to separate the plasma surface interaction in a topological way, let's say, sort of by the structure of magnetic field, from the region in which the plasma is confined and burning. So what I have the time to do today is to discuss a little bit this concept. This is a historical picture, I think is from the 70s. How to face this edge problem. Initially, people had what's called a limiter. So plasma is sort of controlled in the sense of the interaction with the wall by a material limiter. So it's a piece of metal, let's say, either in a poloidal direction or in a toroidal direction. So that defines the first surface of the plasma that is not in contact with any material wall. But of course, it's very difficult to avoid that the plasma has an impact on the material of the limiter, or stated from the other angle, it's very difficult to find a limiter material that's good enough for those issues that we just seen before. So it's not spattered, it's mechanically resistant, it doesn't absorb too much tritium, and so on and so forth. So a much better, or a more modern idea came later on, I guess at the end of the 70s, and say, okay, instead of having the plasma leaning on a material surface, let's divert the field lines out, either by the toroidal divertor, so there would be field lines being if you want, bulging out of the plasma. So this surface is defined simply by magnetic structure, or even a better idea with a diverter all around the direction of the torus here. It's called a poloidal diverter, which basically modifies the field line structure so that some field lines inside never see the wall, and there's a particular field lines which is the first one to have any contact with a material surface here. So this is a concept of a diverter, which will be clearer in the next picture. In the cross section over the poloidal plane. Diverter means the creation of, again, a next point. So the poloidal field goes to 0 here. There's a separatrix line, is a line that goes to the X point. All the field lines outside go to a material target. The field lines inside are closed here, and therefore the plasma in there shouldn't see a material target at all. How does this concept work, or what would we like it to do? The idea here is that plasma comes out by the radial transport. There's a little bit of leakage of plasma outside, and we'll go into the transport issues tomorrow. Anyway, some of it comes out. And then the idea is that by this structure, we redirect the plasma, we take it down through flows that are naturally occurring in this layer, which is called the scrape-off layer. It's a layer that is not confined, it touches eventually the targets of the diverter. So the plasma comes out a little bit here, and the perpendicular transport is compensated by the parallel flow. Now, because of the helical structure of the field, actually it's a long distance from the point in which the plasma comes out, we call it upstream, to where it eventually hits this target, because it has to go around, and then hit the target here. So this long distance is called a connection length, so it's the distance between that point and the point at which the field line touches a material surface, allows a reduction in the temperature from where the plasma is immediately ejected from the core here to the point where it hits anything material. That reduction in temperature is an essential point. Typically upstream here, the plasma edge may be of order of 1 keV or half of keV. And what we want to do is that by collisions, the plasma that flows down here is not a core, very hot plasma anymore. So it undergoes more and more collisions. You want that to become very cold by the time it gets to the targets. Why very cold? Well, very cold of order of a few EVs, because at that temperature, the ionization cross-section becomes smaller than the charge exchange cross-section, and then energy is transferred from ions to neutrals. So in other words, ions come down here. If things are relatively cold down here, energy goes into neutrals. And neutrals are good because they're not then trapped anymore in magnetic field. They go everywhere and they spread the power deposition. So power comes down. We don't want all of it to go on a single point because it would be a power flux enormously high to be able to cope with it with any material surface that we know. It will hit the neutrals, and then the neutrals will spread the power deposition. Then you have a further reduction in the temperature, and recombination. The plasma is sort of dying there, recombination between electron and ions, and so the plasma is not even touching the material surface anymore because there's a recombination going on before it does that. If we are in a good situation in which the cooling is efficient. That situation in which the plasma doesn't touch the material surface anymore is called detachment, and is a situation in which the reactor will have to work in order not to melt the material surfaces. And this is an example, again, is not the dream, is a common way of operating a tokamak with a diverter, with that concept. This is an observation of it. I think it's one of the earliest observations. This is in a German tokamak in Munich. And the detachment is seen as a sudden reduction in the temperature. I said before we want the temperature to go to a few EVs, let's say 5 EVs. So here we are. That's the temperature, both electrons and ions. And then here, electrons and ions are 5 EVs. They recombine. This is the density. They recombine, and then they spread the power deposition. An image, in fact, is from a different experiment, but of the same phenomenon, is shown here. You see here the electron temperature data. It's from a Thomson scattering method. Anyway, it's electron temperature data reconstructed over the X-point region, and you see that it doesn't go higher than a couple of EVs. So plasma is detached there. The diverter is working well. Nothing is happening, nothing is arriving at the target place. Material surfaces are not even touched by the plasma there. So no problem with withstanding of power loads in those areas. And let's see, to conclude today's lecture, I just want to show a few examples of that concept applied to different machines, of which actually only one doesn't exist yet, but the others all do. This is jet, so you see the X point here, and then you need to be able to design specific plates here to get the residual energy. And then you have a particular geometry for flows to take place, and so on and so forth. And the other thing you want, once the particles are down here, you want to solve the problem of the exhaust of particles. We just talked about the problem of exhausting the heat. Now we want to get rid of the particles that are down here. So you have an ideal situation in which compress the particles here, and you can pump them. So this is a cryopump, for example, here in jet. ITER is designed on a similar principle. This is the D3D at San Diego machine. It has even 2 X points in the plasma. German machine, of which we've seen the results. So slightly different variations. There's a lot of studies and investigations going on, including modeling. This is the American Tokamak at MIT with different geometry here, and that's the Japanese one, which was one of the is one of the largest experiments with diverter. So one thing we have not addressed, and I think we can address that tomorrow because it's 12, is what happens during transients. Now we have dealt with a sort of steady situation, but now there is one additional problem, is that the plasma, again, is very prone to instabilities, and they occur when you have gradients in the edge, will eject particles, and then you need to cope with that. So that problem, I think I can discuss starting tomorrow. Tomorrow we'll start from this problem, and we'll go on to then discussing the choice of materials. And then I will discuss the question of plasma transport, how we control the losses of energy and particles. Then what happens in the regime in which the plasma is burning, it's really producing energy, what different physics takes place there. And then finally I will introduce the more directly the new ITER experiment and then the way to the future. So tomorrow we'll start from this problem of the edge instabilities and go on from there. Thank you. They yeah, depends on where, because of course in the center of the plasma is very hot, so their collisions are very rare, and then there is a long time for them to thermalize. In the edge, plasma is very cold, so it becomes bad conductor, lots of collisions, and there's much easier thermalization.
And so when you drive the barrier and you excite the electrons, you use this. So you actually excite the electrons.
You hit the electrons, you're right, and then you have to wait for the electrons to give the energy back to the ions, because after all, the ions are what we want to be hot because they ignite. However, in a reactor, we need also higher densities. And the collisions are proportional to 1 over T to the 3 halves, but also to the density. The denser the plasma, this is more conventional behavior, the denser the plasma, the more collisions. So in a dense reactor plasma, the times for thermalization, or what we say equipartition, in other words, the same temperature to both species, are shortened, and the pulses will be very long compared to what we have today. So say at order 1,000 seconds in ITER, there'll be plenty of time for thermalization to take place. But in ITER, the electron cyclotron heat will not be used actually to heat the main plasma, will be used to cure instabilities locally, as we have just seen. So also because of that problem. Yes?
Yes, I was struck by the fact that in Tokamak there were many analogies with accelerators. And I just wondered whether some stabilities could have the same fundaments or the same basics as those we see in accelerators, like the beta-atom movements. Would you know about studies about that?
I don't think we are in similar regimes, because I don't know the parameters that you mentioned, but
the beta-atom is quite simple. That you look at the individual particle,
yeah,
and then the number of oscillations is just the circumference of the machine is an integer number of the number of oscillations. So therefore, an oscillation would accelerate itself. You see what I mean?
Right. There's analogy of that with the MHD instabilities, but not in terms of single particles, in terms of the overall structure. So, for example, what we call a Q equals 1 means the safety factor equals 1, which means you go once more around the toroidal circumference to get back to exact same position. That's the most dangerous surface that you have because if you resonate with that, of course, you can have a mode growing, and all of these modes happen on either that surface or integer values of that you go twice around, or low order rational values of that you go 2 times around in one direction, 3 times to make 3 turns in the other. So in that respect, it's a similar thing, but this is a macroscopic overall fluid with higher density, very high density of plasma. It's not an individual particle motion that creates the instability. But the issue of the resonance in the toroidal system is similar, yes.